Okay, let's continue with part 2 of this lecture. Okay then. So we're going to cover the second part of this lecture, which is waveguide dispersion. So remember that waveguide dispersion is the second part of chromatic dispersion. Okay, so we have learned about the material dispersion before this, and for waveguide dispersion, basically, uh, this dispersion is I can say due to the mode field distribution, yeah, in the core and the cladding of the fiber. Okay, because we know that for the waveguide, there should be effective refractive index and effective, which is a combination of the index for the core and the clad. Okay, yeah. For what we have learned in material dispersion before, this material dispersion is due to the effect of lambda towards the end, yeah, towards the end, lambda towards the refractive index n. And the same thing is applied for the waveguide dispersion, in which we're going to have relationship between the lambda and also the n effective. So n effective is a value of the refractive index, a combined refractive index between the core and the clad. Yeah. Okay. So that's why when we have a variation of refractive index, effective index and effective, which is due to the lambda, we're going to have a pulse spreading effect, and this pulse spreading effect is what we call as waveguide dispersion. So we can have a look at this diagram here. Okay, this is a diagram that giving us ideas, yeah, on this V value. Yeah, V value. V is the normalized propagation constant, normalized Mode's number, as we have learned in lecture 3 or lecture 4 before. Okay, we can see that the V is changed. Yeah, V is changed regardless of the I can say the Mode's value, the Mode's number. Let's say we consider the M equal to 0. M equal to 0 means that this is the Mode's number 1, or fundamental modes. We can see that the value of V will change accordingly. Yeah, number of the Mode's value B, the V value will change according to the Mode's number. Okay, and this is what we call as the case whereby the N effective will change according to the lambda. Yeah, so we can see that the left hand side is the effective index of the waveguide. Okay, so we can see that there should be the effect of the effective index change with regard to the V or with regard to the lambda straight away. Yeah. Okay. So I'm not going to cover in detail of this waveguide dispersion. Yeah, because the idea is almost similar to this material dispersion. The difference is only on the changes on the N effective and the N. Yeah, for the material dispersion, we have the N. Yeah, N is refractive index of the core. But for the waveguide dispersion, it is the variation of the N effective. Okay, so we have a DM, which is material dispersion, and the DW is for the waveguide dispersion. And the equation for the DW should be same as this, as what we have seen before for material dispersion. The changes will be only on the changes of N with the N effective. Okay, and this is the parameters used to calculate the DW. Okay, DW, where we need to have informations of the core index N1, clad index N2, the lambda wavelength, and also the V. Yeah, V is the V number, yeah, the V number, and also the B, which is a normalized propagation constant. But to be frank with all of you, somehow the waveguide dispersion, the effect of waveguide dispersion can be ignored. Yeah, most of the time we are not so much interested on this waveguide dispersion because the value is quite small. Yeah, and in such a way we can ignore the effect of waveguide dispersion. So I can say that most of the time in chromatic dispersion, our interest will be on material dispersion. Yeah. Okay. All right. So this is the case. In order for us to calculate the chromatic dispersions here, we can see that in general, the chromatic dispersion parameters DC equals to the dm plus dw. The dm is matter dispersion parameters and dw is the waveguide dispersion parameters. And from here, we can calculate the value of pulse spread per unit length, in which we can substitute the value of a matter dispersion parameters as this one, which is a summation of the dm and dw, and this will give us your pulse spread per unit length. Okay, this diagram is basically a diagram used to show the effect of chromatic dispersion, both material and waveguide dispersion. Okay, we know that this is the line here. Okay, this is the line here that gives us the matter dispersion, and we have seen this line before. That this is we are going to have a 1276 as a zero dispersion wavelength at this point. That will give us the d material or dm equals to 0. This line here that we have, this line is a very small line here. So this is basically waveguide dispersion, waveguide dispersion. Okay, somehow when we add the dm and the dw graph, we can have a new line here. Okay, this line is a new d, which is a summation of both dm and dw. And from here, we can have a new zero dispersion wavelength located at 1310 nanometer or 1310 nanometer. Okay, so this zero dispersion wavelength at 1310 nanometer is obtained when we consider a summation effect, a combination effect of both metal dispersion and waveguide dispersion. Okay, yeah, right. So that's why we have been work in terms of this commercial application. We have applied or we have used a 1310 nanometer as the wavelength for this communication, optical communication, due to this effect. Because at 1310 nanometer, the dispersion or the chromatic dispersion value is 0. Okay, that's why, that's why we have been work previously at 1310 nanometer wavelength of operation. Okay. Right. Okay, let's proceed further with these informations. Okay, so for the pulse spread reduction, so there are a few methods that can be applied to reduce the pulse spread, due to this chromatic dispersion. We know that the effect of pulse spread will be on this bandwidth, or it can be said bit rate reduction. Okay, bit rate and bandwidth is similar. Okay, so we know that the effect of pulse spread will be reduction of the bandwidth of bit rate in such a way. When we have a reduction of bandwidth, the capacity will also be reduced. Yeah, that is we've understood these issues clearly before. Okay, and these are the methods that can be used to reduce the pulse spread. Number one, is by operating at lambda ZD, which is dispersion wavelength. Okay, so as we have learned before, we can use we can use a lambda at zero dispersion wavelength, so that the dispersion effect can be ignored. Or you can also work at or we can also use a very coherent light source, very small delta lambda. Okay, so either to operate at lambda ZD, or to operate or to choose a very small delta lambda. Okay, and we have seen before in this example, in present example, that if you have a small delta lambda, the pulse spread will also be reduced significantly. Okay, so this is the first method. Second method is by we know that the lowest attenuation that we have covered so far in lecture 5 is 1550 nanometer. Okay, we have agreed on this wavelength, which is having lowest attenuation because of very small hydroxyl attenuation and very small Rayleigh scattering attenuation. That's why we are having lowest attenuation of 1550 nanometer. So previously, from this slide, from this diagram, we know that zero dispersion effect due to the summation or combination of both material dispersion and waveguide dispersion we can have zero dispersion at 1310 nanometer. Okay, somehow by applying this method, we can also shift, we can also shift this dispersion value to a 1550 nanometer. Yeah, so by using a dispersion shifted fiber, okay, this is special fiber that can be used. Yeah, by using a dispersion shifted fiber, we can we can shift this zero dispersion wavelength to a 1550 nanometer. Okay, so that's why I mentioned here that we can further works at this lowest attenuation region of 1550 nanometer by simply shift the dispersion curve to these zero dispersion wavelength at 1550 nanometer, in which these special fiber optics can be used to achieve these ideas, yeah, which is to shift the lambda ZD to 1550 nanometer, which is by using the first one, a dispersion shifted fiber, or dispersion flattened fiber, or dispersed cladding fiber. So these are special fibers that can be used to realize this idea, yeah, of having dispersion, or sorry, so shifting value of zero dispersion wavelength. Okay, so I'm not going to cover this in detail on how the operation of this dispersion shifted fiber, dispersion flattened fiber, and dispersed cladding fiber. But if you're interested on learning the ideas on how these fibers can be used to shift the dispersion curve, so you can have a read at any textbook. Yeah, hopefully you can get some ideas on this fiber, special fiber optics structure. Yeah. Okay, so now we're going to have these summaries on the fiber dispersion in total, which is a combination of lecture 6 part 1 and lecture 6 part 2. Okay, so we have now conclude that the pulse spread delta tau, which is based on the non-overlapping assumption, owing to both intermodal dispersion and chromatic dispersion, okay, shall be given by this equation. Okay, so total dispersion, delta tau squared, shall be equals to delta tau, which is due to intermodal squared, plus delta tau due to chromatic dispersion squared. Okay, so in terms of RMS pulse spreading, we're going to have this equation, so about similar. So total RMS pulse spreading squared equals to intermodal RMS pulse spreading squared plus chromatic RMS pulse spreading squared. Okay, yeah, so these are the equations that can be used to calculate the total dispersion in our fiber optics by a combination of both intermodal dispersion and chromatic dispersion. Yeah, so when we are requested to find the total dispersion, so you have to use either this equation or these equations, depending on the information given. Yeah. Okay, so for two types of fiber optics here, so I give you a conclusion or summary. When we have a multimode fiber, whether it's step index or gradient index fiber, the total dispersion shall consider both intermodal effect and chromatic effect. Yeah, modal effect and chromatic effect. But for a single mode fiber, we know that there should be no intermodal dispersion. So your pulse spreading or pulse broadening or pulse dispersion shall be only due to chromatic dispersions only. Yeah, which is having either metal dispersion or waveguide dispersion. And as I mentioned before, most of the time, our interest will only be on metal dispersion. Okay, so that should be the summary of lecture 6, basically. Any questions so far on this fiber dispersion? No?
No, doctor.
No, yeah. Okay, so let's have a look at these examples, few examples before we end the class today. Okay, the first question is, we are having 2 kilometers length of multimode fiber. Yeah, this is multimode fiber, yeah. Has a modal dispersion of 1 nanosecond per kilometer. Okay, this is intermodal dispersion, 1 nanosecond per kilometer, and a chromatic dispersion of 100 picosecond per kilometer nanometer. If it is used with an LED of line width of 40 nanometer, okay, number one, what is the total dispersion? Okay, so this is to based on the equations that we have seen before. And number two, calculate the bandwidth of the fiber. Okay, so I think to calculate the bandwidth, you have to rely on the bitrate equation that we have seen before. Okay, so let us have a look at this example. Remember, for these questions, you are having a multimode fiber. Both are having intermodal dispersion and chromatic dispersion with the given line width value or spectral line width value. So first question, find the total dispersion. Second question, calculate the bandwidth. Okay, so let's have a look at the solution for this example now. Okay, so the solution is here. Okay, so we are given these conditions, but it doesn't mention in the question whether we are dealing with the RMS or not. Yeah, so what we have to do is that we assume that this is non-overlapping assumption. So for this, we have a delta t. Yeah, so delta t for the intermodal will be 2 kilometer multiplied with this. I can say the dispersion parameters 1 nanosecond per kilometer. So we have the intermodal dispersion or pulse rate due to intermodal dispersion is 2 nanoseconds. Okay, and for the chromatic dispersion, the pulse rate is 2 kilometer multiplied with 100 picosecond per nanometer per kilometer. This is your parameters multiplied with the line width, which is 40 nanometer. So we're going to get 8 nanoseconds. Yeah? So remember where these equations come from. And these equations come from, remember, the dm multiplied with the L multiplied with the delta lambda. I repeat again, yeah? So delta T here comes from the dm is 100 multiplied with the L, which is 2 kilometers, multiplied with the delta lambda, which is 40 nanometers. So that will give us 8 nanoseconds. Okay, and for the intermodal, simply we multiply the intermodal dispersion parameters with the length. So we're going to get 2 nanoseconds. Yeah? So that should be the value of your intermodal dispersion and chromatic dispersion. So to find the total pulse spreading, simply we use the equations that we have done before. Yeah, delta t squared equals to delta t model squared plus delta t chromatic squared. So by substituting these two information, you're going to get the delta t will be 8.24 nanoseconds. So this will be your total pulse spreading due to a combination of intermodal and chromatic dispersion. Okay. Right, and this is the equation to calculate the bandwidth or the bit rate. So in this condition, we assume that the bandwidth and the bit rate are the same. Okay, so BT equals to 0.5, or I can say 1 over 2 delta T. Okay, 1 over 2 delta T. You can refer to the summary in lecture 6 part 1. For the case of non-overlapping assumption, the bit rate is 1 over 2 delta T. So delta T has been obtained is 8.24. So end up your bit rate or bandwidth is 42.48 megahertz. Yeah, so this is your bandwidth for the given information. Yeah, 42.48 megahertz. Okay, hopefully you understand about calculation of the bit rate or the bandwidth. Yeah. Okay, so let's have a look at this second questions here, which is we're having a multimode step index fiber. Okay, so we are having a multimode step index fiber with a numerical aperture of 0.3 and a core refractive index of 1.45. The material dispersion is 250 picosecond per nanometer kilometer, which makes material dispersion is the totally dominating chromatic dispersion mechanism. Okay, means that for this multimode step index fiber, your dominating chromatic dispersion comes from material dispersion. Yeah? Okay, estimate number 1, total RMS pulse broadening per kilometer when the fiber is used with an LED source of RMS spectral width of 50 nanometer. Part B is corresponding bandwidth length product of the fiber. Okay. Okay, somehow quite similar with the above questions. We are having a multimode step index fiber. Okay, we are given the numerical aperture 0.3 and the core index 1.45. Okay, what's the purpose of giving this NA and the core index. Okay, the purpose of giving this is for us to calculate the intermodal dispersion value, yeah? Intermodal dispersion value. So you can refer to the notes before on how to calculate the intermodal dispersion value. Okay, and also we have a material dispersion in this particular case, right? So you need to calculate what should be the RMS pulse broadening per kilometer when we have the spectral line width or the FLAD is 50 nanometer. And from this information, we can then calculate the corresponding bandwidth length product. So let's have a look at the solutions for this example, yeah? Okay. Okay, right, this is the one. Right, so there should be two pulse dispersion or dispersion contributors here. The first one is intermodal dispersion. Second one is a material dispersion. So you have to calculate the pulse spreading due to this type of dispersion effect. Yeah. So what I did here is I concentrate for the first one, which is on the material dispersion. So we have to use this equation here, which is based on the RMS statistical equation. So sigma m over L, which is RMS pulse broadening per kilometer, will be dm, which is given to be 250 picosecond per nanometer kilometer, multiplied with delta lambda. Delta lambda is given to be 50 nanometer, and you're going to have the sigma m is 12.5 nanosecond per kilometer. Okay, this is the one, yeah? This is the equation, the value obtained for the first factors of dispersion, which is material dispersion. For the second one, which is due to intermodal dispersion, we have learned that the RMS pulse broadening is to be based on these equations, yeah? Yeah, you can refer to the lecture 6 part 1, where we need to use information of NA, numerical aperture, and also the N1, which is your core index. So by substituting the informations given, you can know that you can obtain that the pulse broadening RMS due to intermodal dispersion will be 29.9 nanosecond per kilometer. Okay, so now you understand that in multimode fiber, there should be two effects of dispersion. In this example, we have material dispersion and we have intermodal dispersion. So calculated earlier that for the material dispersion, the pulse spread RMS is 12.5 nanosecond per kilometer, whereas for intermodal dispersion, the RMS pulse spread is 29.9 nanosecond per kilometer. So from these two values obtained, we can calculate the total pulse spreading, which is based on this equation straight away. Okay, so total RMS pulse broadening per kilometer will be this equation, 12.5 squared plus 29.9 squared, square root will give us the total attenuation, total pulse spreading, which will give us 32.4, yeah? 32.4 nanosecond per kilometer. So this is the total pulse spread due to effect of both intermodal dispersion and material dispersion, yeah? Okay, so from this delta T, we can use it to calculate the bandwidth or bit rate. Okay, so we can use this equation because you are having the RMS value of pulse spread. So the bit rate will be 0.2 over total pulse spread, which is 32.4 nanoseconds. So end up your bit rate or the bandwidth is 6.2 megahertz. So in a bandwidth length product, it should be 6.2 megahertz kilometer. Yeah, because you're not given the length straight away. So we assume that it's 1 kilometer length. So the bandwidth length product simply will be 6.2 megahertz multiplied with the length of 1 kilometer. So that will give us the bandwidth length of 6.2 megahertz kilometers. Yeah. Okay. Hopefully you understand these issues clearly. Yeah. Okay. So let's have a look at another example. Okay, this is the one. Right. We're having a multimode step index fiber again, which has a relative refractive index difference of 1% and core refractive index 1.46. So it was given here that the maximum optical bandwidth that can be obtained with a particular source on a 4.5 kilometer link is 3.1 megahertz. Okay, so we are given a case of multimode step index fiber. We are given the delta, yeah? Delta will be a relative is different. Delta is 1% or 0.01 and the core index is 1.46. So the maximum optical bandwidth given or the maximum optical bandwidth that is obtained with a 4.5 kilometer length is 3.1 megahertz. So this is the maximum optical bandwidth that can be obtained. So part A, determine the RMS path broadening resulting from chromatic dispersion. Yeah, resulting from chromatic dispersion. Okay. Number 2, estimate RMS spectral width of the source if matrix dispersion parameter is 90 picosecond per nanometer kilometer at the operating wavelength. Okay, so how to calculate this number 1, which is the RMS path broadening, and number 2, if now given that the material dispersion is 90 picosecond per nanometer kilometer, what should be your RMS spectral width? Okay, so to answer the first questions here, we know that we are having a multimode step index fiber, right? So for multimode step index fiber, we know that the dispersion will come from two factors. The first one should be intermodal, yeah, and second one should be a chromatic, yeah, chromatic dispersion. So the question now is, what is the RMS path broadening resulting from chromatic dispersion? Okay, so we know that the bandwidth given is 3.1 megahertz. So from this given bandwidth, we can use it to calculate the total path spreading. Am I right? Yeah, because we know that the relationship between the bandwidth or the bit rate and the path spread is given by bandwidth or the bit rate is 0.2 divided by the total path spread, because we are referring to the RMS, yeah, RMS value. So bandwidth equals to 0.2 divided by the path spread. So from here, we can know what should be the value of path spread. So this path spread is the total path spread, right? And the total path spread is a summation of the path spread due to intermodal effect and chromatic effect. So in these questions, we have given the delta and the N1 or the core index, in which this enables us to calculate the path spread due to intermodal. So since we know the total path spread, we know the path spread due to intermodal, so we can use these two information to calculate the path spread or path broadening due to chromatic dispersion. So that's the idea, yeah? So first of all, need to obtain the total path spread due from the given bandwidth, then calculate the path spread due to intermodal dispersion. So from these two informations, then only you can calculate the chromatic dispersion, the RMS path spread due to chromatic dispersion, yeah? Okay, I think for part B should be easier, because from this information, number 1, you can use it to calculate the spectral width of the source, because your matrix dispersion has been given straight away, yeah? Okay, let's have a look at the solutions to make it clearer for us on these ideas, yeah? Okay then, so we're having these questions here. Right, we have this information, multimode fiber, delta is 1% or 0.01, core index is 1.46, bit rate is 3.1 megahertz, and the length of 4.5 kilometer. So from these equations, the RMS path broadening due to model dispersion or intermodal dispersion, we can calculate that the path broadening RMS based on this equation supposedly, because the delta is given, N1 is given, so we can have it to be 63.22 nanoseconds, yeah? Right, this is the total dispersion due to model or intermodal dispersion. Okay, and from what we have learned before this, the total path spread can be obtained by this equation. We know the bandwidth of 3.1 megahertz. So the total path spread can be calculated from this equation, which will subsequently give us 64.52 nanoseconds. So that should be your total path spread. So from these two informations, path spread total and path spread from intermodal, you can use it to calculate the chromatic path spread. So chromatic path spread will be this equation, sigma total squared minus sigma intermolar square root. So end up, you're going to get your chromatic pulse rate RMS is 12.89 nanoseconds. Okay, so that's how you calculate the chromatic dispersion pulse rate, RMS value, 12.8 nanoseconds. And from this total pulse rate of 12.8 nanoseconds, you can straight away use this equation, yeah, to calculate the delta lambda, because we know that the dm has been given of 90 picosecond per nanometer kilometer, length has been given of 4.5 kilometers. So straight away, by substituting all the informations given and calculated previously, your delta lambda or RMS spectral width will be 3.18 nanometer straight away. Okay then. Okay, hopefully you understand these topics clearly. Yeah, on these issues of intermolar dispersion and modal dispersion together with chromatic dispersions. Yeah. Okay, I think I'm going to stop here because for the last one here is about similar to the above examples. Okay, because we're dealing with single mode fiber. For single mode fiber, we know that it can only be a chromatic dispersion only. There should be no intermolar dispersion. So we are given a bandwidth length of 10 gigahertz per kilometer, 10 gigahertz kilometer, and we are given a 40 kilometer length. So from these informations of 10 gigahertz kilometer and 40 kilometer length of fiber link, you can calculate the bandwidth straight away. Yeah, bandwidth can be calculated. So from the calculated bandwidth, you can then use it to find the RMS pulse broadening. Yeah, because bandwidth equals to 0.2 divided by sigma t. Sigma t is the total pulse broadening. Yeah, so from here you can calculate the RMS pulse broadening. So the detail of this solution can be obtained from the solution file which will be given to you after the class later on. Okay, so that's the end of chapter 3. Okay, so we have covered chapter 3 successfully. So what we have done so far for the first 5 weeks of this course is on understandings about the optical fiber itself, yeah, the channel itself. Yeah, so we have understand the fiber optic structure, we have understand how the light propagates in the fiber, and we have understand what causes the attenuation and dispersion in the fiber optic structure. So next week onward, we're going to cover on one component of optical system, which is the optical sources. Okay then? Okay, any questions for this lecture before we end the class today?
No, Doctor.
Okay, so hopefully there's no questions from the floor. So if there's no question, I think I'm going to stop the class now, but I'm going to share again the QR code for attendance. Okay, I'm going to upload the notes, the solutions for this lecture after this.